All right, so this is going to be a video about rational functions and their graphs. So there's going to be a lot we're going to look at here. Namely, we're going to determine the domain of a rational function. Before that, we're actually going to talk about what a rational function even is. Then we're going to determine the vertical, horizontal, and or slant asymptotes of the graph of a rational function. All right, first thing is, let's talk about what a rational function even is. A rational function is a ratio of any two polynomials. That is, a rational function is the function of the form this right here, where P and Q are polynomials. So if you remember from the last few sections of what a polynomial is, if you just divide any of those two polynomials, then you end up with a rational function. But what you're dividing by, the Q, has to be not equal to 0, because then you're dividing by 0, and you can't have that. Okay, the domain of the rational functions is the set of all real numbers for which the denominator is not 0. So to figure out which ones are in a certain domain, what values are in a certain domain, we're going to figure out which ones would cause a division by 0, because obviously those would not be counted. Okay, the domain of a rational function is the set of numbers that are not restricted values. So there are certain values you cannot put in for a specific value in the denominator, because then it would cause a division by 0. And as we talked about just a second ago, you can't have any divisions by 0. Okay, this next section, as you can see, there is a number of different rational functions. You can see this is a polynomial divided by a polynomial, so that's a rational function. Polynomial divided by a polynomial, same thing. This one's a polynomial divided by another polynomial, but it's dividing really by 1. Same with this 5 over 1. So the 1, you're still dividing by a polynomial because 1's a polynomial. So essentially, even if there is no fraction, where you don't actually see the fraction line on it, it can still be a rational function, because a polynomial is technically a rational function where you're just dividing by 1. There's a thing called a reciprocal function. It's y equals 1 over x. It's the simplest rational function probably that you can have. The domain on it, as you can see from the graph, you can figure out the domain. The domain is all the x values from negative infinity to 0, and then from 0 to infinity. The reason you cannot have 0 is because if this x was 0 right here, you'd be dividing by 0, and you can't have a division by 0. It's a restricted value. The next thing is the range. It is from negative infinity to 0, and then you can't be 0, so then it skips over that from 0 to positive infinity. So as you can see, the y is never equal to 0 right here, nor is the x actually equal to 0, like we just talked about a second ago with the domain. The reciprocal function is an odd function, since its graph is symmetrical about the origin. Okay, if you go to infinity on the left or the right, the y ends up going to 0. As you can see right here, it's going to 0 here. It's also going to 0 up here. Okay, as x goes to 0, you can see the y is going to infinity over here, and then negative infinity over here. So just a brief explanation of the features of this graph. The reciprocal function and its graphs have some of the properties that we will see over and over again as we continue to study more rational functions. So the ideas that we just talked about, the non-divisions, you can't divide by 0, that sort of thing, is going to be talked about in the next few examples that we're going to do. First thing we're going to go over here, asymptotes. So for vertical, the main thing that you want to understand with vertical is basically what it says right here. The main thing you need to understand with vertical asymptotes is if the y values grow without any bound. So it's getting closer and closer to a. So if I had to draw a picture of this, it would look something like this. Like imagine I had an xy coordinate plane, and then I drew a graph here where, let's just say this is A. If A has a vertical asymptote, the graph might look something like this, where it goes from either end here, and it's never actually reaching A. The x is never equal to A, because they're going to positive or negative infinity. Now you could have two graphs where, one of them goes up like this, and the other one goes up like this as well, instead of the other one going down. You can have one going downward like this, and then the other one going upward, or they can both be going downward as well. Either way, there's many different versions of asymptotes that you can have. So again, real quick, you can have ones that do this. So vertical asymptotes that do this. They can do the opposite of this. So maybe one's here and the other one's here. You still have that vertical line that it's never reaching. You can have ones where they both go upward. Still again have that vertical line that it's never reaching. And then they two going downward as well. And again, those are all the types of vertical asymptotes that you can have. The main thing for calculating vertical asymptotes is any values that you plug in for x that cause a non-zero divided by 0. This is the key for vertical asymptotes, a non-zero over 0. So if you have 3 divided by 0, 4 divided by 0, negative 10 divided by 0, as long as it's not 0 over 0, it's going to be a vertical asymptote. If it is 0 over 0, that's going to be a whole. That's going to be talked about in a different section, so we don't really need to worry about it here. We just need to know that it's not actually an asymptote if that happens. Let's actually look at some graphs to understand this a little bit more. So let's imagine we have a graph that's, let me blow this up a little bit. So let's imagine we have a graph that's y equals f of x is equal to 3 divided by x minus, I don't know, let's just say 2. Okay, if you notice, based on this graph here, let me zoom out a little bit, there is a vertical line of x equals 2 right there that you could see. Here, let me actually make this dashed, so you can kind of see this a little bit more, where it's going up on both sides, but it's never actually reaching that 2. The vertical asymptote is happening at x equals 2. You can see right there at x equals 2. If I zoom out, it looks like it's touching it as I go further and further down, but if I zoom in, you can see it's off by a little bit still. If I go back here and do the same thing up here, it looks like it's getting closer and closer and closer and closer, but if you zoom in, you'll see it's actually separated by a little bit. It's getting infinitesimally closer to it, but never actually reaching it that is what a vertical asymptote is. And if you notice, this right here, x minus 2, if I plugged in 2 there, I'm dividing by 0. If I change this to any other value, you'll notice there is no vertical asymptotes anywhere else. It specifically happens at 2 because 2 would be causing the division by 0. Okay, there's no other asymptotes anywhere else. But if I added another factor to the bottom here, so I'm going to put some parentheses here and just do like, I don't know, x plus 1. Now if you notice, what would cause x plus 1 to be equal to 0? Well, negative 1. So if I write x equals negative 1, you'll notice now there's a vertical asymptote at x equals negative 1. I'm going to make this dash just so it kind of matches it. And you can kind of see it makes the same kind of pattern. It looks like it's intersecting it eventually, but it never is. It's just getting infinitesimally closer to it without ever reaching it. So you can have as many vertical asymptotes as you want, essentially. But if I end up putting like an x plus 1, like a common factor at the top here, you'll notice now the vertical asymptote disappeared. Okay. If you notice at x equals negative 1, it's no longer there. But if you actually click over here on Desmos, you can actually see it's undefined. It's a hole. So this is what I was kind of talking about before. If it's not a 0 over 0, then there's going to be a hole. Now, if you plug negative 1 into this f of x equation right here, you're going to get literally 0 on top because negative 1 plus 1 is 0. You're going to get 0 on the bottom because this right here. So you get 0 over 0. That's going to be a hole. It gets rid of that asymptote. But if I get rid of this x plus 1 and let's just say we change it to x, you'll notice we still have both of those vertical asymptotes. Okay. Say I change it to x minus 2. Again, that asymptote on the right this time is going to go away because we have a 0 over 0. So watch minus 2. Now you'll notice this blue line right here does not have an asymptote, but it has a hole right there because it causes a 0 over 0. So anytime you have a 0 over 0, it's not going to be a vertical asymptote. You have to make sure you check. All right, let's look at some examples here. Let f of x equal this rational expression right there. And it says determine the vertical asymptotes of the graph of f. Now we cannot be dividing by 0. So what we need to do is set the denominators equal to 0. And then we're going to figure out where those vertical asymptotes are because it's, non-zero over 0. So we have to figure out what causes a division by 0. Well, x equals 3 is one of the answers. X equals negative 2 is the other answer. But you have to make sure, are these both non-zeros over 0? So you have to plug them in to the f of x function. So if you do that, f of 3 is equal to 10, because it's 9 plus 1 up top, divided by 0. Well, this is a non-zero over 0. Therefore, x equals 3 is one of the answers. So I'm going to highlight that. I'm going to do the same thing with the other one. So f of negative 2 is going to be 4 plus 1 is 5 divided by 0. So again, we have a non-zero over 0, which means x equals negative 2 is the other answer. So there's 2 vertical asymptotes on this. Now, just for fun, let's actually graph this out and check for ourselves. Okay, so now based on this graph, if you graphed x equals 3, if you graphed x equals negative 2, you'd see that it's the 2 vertical asymptotes, and we're good to go. There's no holes on this that we have to worry about. All right, the next one, determine the vertical asymptotes of the graph of g. Okay, so first thing I'm going to do is set the denominators equal to 0, add 1 to both sides, add 5 to both sides, and you get x equals 1 and x equals 5. Well, let's figure this out now. Let's try g of 1. If you plug g of 1 in, you're going to get 2 times 1 minus 2 is 0. Uh-oh, we're getting 0 on the top and 0 on the bottom, which means that's a hole. So that is not one of the answers. Now we can do the same thing with the 5. Plug the 5 in, and you're going to get 10 minus 2 is 8 divided by 0. That one actually does work. So you can see whatever causes a 0 over 0 is not an asymptote like I showed you before. With those graphs, it causes a hole. Because it's a hole and it's asking for vertical asymptotes, we do not write that down as the answer. All right, the next thing, the line y equals b is a horizontal asymptote of the graph of f if the y values of f get closer and closer to the number b as the x values grow without bound positively or negatively. Okay, so let's go over some horizontal asymptotes with the graphs just so this makes a little bit more sense. All right, here's a pretty simple rational function that we're looking at here. And the main thing with horizontal asymptotes that you want to look at is you want the x basically to be going to either positive infinity or negative infinity or both to try to figure out what this is doing. So f of, let's just say 1. Well, that's not infinity. Okay, we need to plug in values that are way bigger than 1. So what you can actually do here is just keep plugging a bunch of zeros in and notice the trend. You'll notice this is getting closer and closer to 0. So y equals 0 is actually the horizontal asymptote. As you can see, if I get closer and closer to infinity, that's closer and closer to the right. That just means you just keep moving to the right. And if you notice, it looks like it's, kind of touching, but if you zoom in, you'll notice it's still off by a little bit. Okay, they are going to match on both sides for rational functions. So if you do the same thing over here to like negative infinity, you'll notice it does the same thing. It's getting closer to it, but never actually reaching it. Okay, if I put a negative in front of here, you'll get the same kind of thing. It's approaching 0. So with horizontal asymptotes, basically what you want to be doing is the x's should just be getting bigger and bigger and bigger and bigger because they're going to infinity, or they're going to negative infinity. Now, since they're going to infinity or negative infinity, you need to worry about the term with the biggest exponent, or the degree. So one thing that I want you to notice on this, the 4 over x minus 1, the degree on the top is 0. It's 4x to the 0 power. The degree on the bottom, though, is x to the first power. So the degree on the bottom is actually bigger than the degree on the top. Therefore, it's always going to go to 0. And that's one of the rules that I want you to remember. So if the denominator has a bigger degree, then y equals 0 is the horizontal asymptote. Now, you might be thinking, well, what if they're equal? Okay, we just did if the denominator is greater. Well, if they're equal, the horizontal asymptote is whatever the leading coefficients, you just divide them out. Okay, so what do I mean by leading coefficients? Let's look at the graph. Imagine if I put a x right here. Now the degree on the top is equal to the degree on the bottom. They're both 1. By the way, this minus 1 doesn't really make much of a difference. I can also put a plus 3 in here. You want to look at whatever term has the biggest exponent. In this case, it's 4 times x, and in this case, this x. So you really don't even need to worry about this minus 1 and this plus 3, because you're going to get the same answer no matter what, because you're going to infinity. The 3 and the 1 can basically be ignored. They're basically meaningless. So now, if you did the same thing, you just looked at the biggest power, the x and the 4x, well, if you just divide those out, you get 4. 4x divided by x is 4. If you put 4 in here, you'll notice 4 is actually the horizontal asymptote there, because they have equal degrees. The numerator and the denominator have equal degrees. So if I change this to, I don't know, a 2, and change this to a 3, now it's just going to be 2 over 3. So if you notice I do 2 over 3, and you zoom in here, you can see that that's clearly the horizontal asymptote. Okay, what happens if I made this squared, and this bottom one squared? Well, if you notice it's the same thing, it's still 2 over 3. Horizontal asymptote did not actually change. It is still 2 over 3, even though they both became squared. If they both became 3, same thing. And still 2/3. Now, if I added some more stuff to it, some more character, minus 3x, let's just do 3x squared plus 4x, it doesn't actually matter. The only thing that matters is which term has the highest exponent. So in this case, it's still x to the 2x to the third and 3x to the third. That's just 2 over 3. Again, it still ends up being 2 over 3. Okay, it does a little bit more, stuff here where it goes up and down a little bit, but it still ends up, if you look over here, it still ends up approaching it, never actually reaching it, but still approaching it nonetheless. Okay, it does not matter all this other stuff. For all intents and purposes, I can just delete this. And if you notice, you still get 2/3. It still has a y equals 2/3 because it's looking at the biggest power for the numerator and the denominator. Now, if you look at this one up here and we just make the top one bigger, so now you'll notice that there is no longer a horizontal asymptote. In fact, it's a slant asymptote. It kind of bends up here and goes up to infinity. Okay, it doesn't just flatline on either end, actually. We're going to talk about slant asymptotes in just a second, but let's do some horizontal asymptote problems a little bit first, and then we'll go to the slant asymptotes. And just to kind of reiterate what I just said, if the degree of the numerator is greater than the denominator, so now if it's bigger on top, there is no horizontal asymptote because it forms that slant asymptote. All right, let's do some examples that illustrate all of these. This first one, again, for horizontal asymptotes, all you have to do is get rid of all of this other stuff. It's not as important. And then just look at this, 3x squared over 2x squared. Just get rid of the x squareds, and now you have y is equal to 3/2, and that ends up being the answer for that horizontal asymptote. Okay, the next one, we're going to do a similar thing. There's all this extra stuff. We're going to infinity, so it doesn't matter. We just need to look at the biggest infinity on top and the biggest infinity on the bottom. Now, if you notice, the power on the bottom is actually bigger. So since the power is bigger on the bottom, we're going to be dividing by a bigger and bigger infinity each time. The answer is just going to be 0. So if the degree on the bottom is bigger, it's always going to be y equals 0. This last one says, explain how you know that the graph of f of x has no horizontal asymptote. Well, you know it has no horizontal asymptote because the top part has a higher degree, the numerator has a higher degree than the denominator. So because of that, there is going to be no horizontal asymptotes. Because the degree, the numerator degree, I'm just going to write numerator degree, is greater than the denominator degree. So whenever that happens, there is not going to be a horizontal asymptote. Okay, a non-horizontal or non-vertical line that approaches as the x values grow without bound is called a slant asymptote. We kind of talked about that just a second ago. Okay, this is going to happen when the degree of the numerator is exactly 1 more than the degree of the denominator. So if the degree on top is greater than the degree on the bottom by 1, you're going to have a slant asymptote. And the easiest way to find slant asymptotes is you're going to have to carry out long division. So it's actually a callback from the stuff we were doing before. So to figure out the slant asymptote of this and the vertical asymptote, it wants both. So it wants the slant asymptote and the vertical asymptote. What we're going to do is we're going to first do long division on it, and then we're going to find the vertical. Actually, let's just find the vertical asymptotes like what we just did before. So essentially what you're going to do is set the denominator equal to 0 and solve. I'm going to solve this by factoring. Okay, and the two answers you get is x equals 0 and x equals 1. Okay, test the 0 and the 1 in this. You're going to get non-zero over 0 for both of them, so that is the vertical asymptote for this. But the main part that we need to worry about is this slant asymptote, because it's a lot more involved, has a lot more steps, because we have to review long division. First thing we're going to do is we're going to write x to the third plus 3x squared plus 1, and we're dividing this by x squared minus 1. First step is line up the leading terms, the x squared and the x cubed. What do you multiply x squared by to get x cubed? Well, an x. And then we waterfall this down, x to the third minus x squared, subtract, cancel, cancel, plus, plus, 4x squared plus 1. From here, we're going to multiply this 4 by this x squared and by this minus x here, and you're going to get 4x squared minus 4x, parentheses, and then subtract, cancel, cancel, plus, plus, and then you're going to get a 4x plus 1. Now, you can't multiply anything by that x squared to get that 4x plus 1, so it ends up just being the remainder, and you can do the remainder over whatever you're dividing by. But the main thing that we need here is just this first part here, x plus 4. That's actually the slant asymptote. That's how you find the slant asymptote. You do long division, and whatever part does not have a fraction, so this part just gets thrown out basically, whatever that remainder part is, we just don't ignore the remainder part, and the slant asymptote is going to be the rest of the part that's there. So x plus 4 ends up being your answer for this. So what we're going to do is actually I'm going to graph this out so you can kind of see it for yourself, see what it looks like, and see how this slant asymptote thing works. So here we go. So here's what that graph looks like if you plot it out in Desmos. It's not the best looking graph in the world. There's got a lot of moving parts to it. Let's do x equals 0. Okay, you can see there's a vertical asymptote there. We could do x equals 1. You can see that there's a vertical asymptote there. And then last but not least, we're going to do y equals x plus 4 for the slant asymptote. And you can see that the slant asymptote kind of reacts the same way as the vertical and the horizontals. It's getting infinitesimally closer to it, but if you zoom in, you'll see it's not actually reaching it. It does it the same way on the other side as well. Zoom in here, you can see, so it's not quite reaching it, but it's getting infinitesimally closer to it. So that's basically how the slant asymptote works when you actually graph it out. So that's rational functions in their graphs. Hopefully you're able to figure out vertical, horizontal asymptotes as well as slant asymptotes of rational functions. If you have any questions about anything in this video, let me know.